So we do want to kind of address overall processes as we go through this. We should process the question first as I slowly start thinking about it and warm up. If you have 100 milliliters of the 0.1 molar tris buffer at pH 8.3 and you add 3 milliliters of HCl, then what's the new pH? What would we expect the new pH to be?
Lower.
Should it go lower because you're adding acid? Okay. So it started at 0.1 molar, but to get to a pH of 8.3, is it going to be exactly that? Okay, so what we're looking at is your equation. You've got your tris with your hydrogen, which is in equilibrium with your tris without the hydrogen. So your buffers are all have an acidic hydrogen on there. So it's just a question of where it's located. Where did I get this question from? I wonder if I just made this up. I think I just made it up. Some of this doesn't quite make sense. So if we assume we're at 0.1 molar tris to start with, which is a bit of a stretch, but if we assume that, what's the tris H concentration?
pH is equal to pKa, then it's going to be the same.
Okay, we're at the half equivalence point. The pH equals the pKa. Okay, so to figure that out, what you have to remember is your Henderson-Hasselbalch equation, which I am horrible at remembering, but I will make you manipulate it as far as understanding particularly the half equivalence point and those kind of evaluations off of it. Because I'm going to make you interpret it, I'm also going to make you, or could make you memorize it, but as I've already suggested, I can't memorize it, so what I'll do is provide that on the exam. I won't expect you to go digging for that. So we got our pKa, it's plus log of our base over our acid, is that right? Okay. So we have an initial condition. We know that our concentration of our tris H and our tris are the same. Oh man, I went all sorts of crazy on this. That was awful. It's going to involve a lot more calculations than I wanted. That tells us the amount of moles to start with of our tris and tris H are the same. Okay, if we're at that pKa, okay, or that pH to start with. Okay, so if the pH equals our pKa, slide that in with a different color, then we know that the log of our base over our acid must be equal to 0. For that to be the case, A minus and HA have to be the exact same thing. Otherwise, it doesn't work. Okay? So, to simplify, we're going to end up just saying that the concentrations of our tris and our tris H are ultimately going to be the same. Okay? And we won't worry about going through and calculating those. We then go through and add acid. What's the acid going to react with? Okay, the basic version of our base, so the tris, and go backwards. Okay, so what we have to go through and do is a non-equilibrium calculation. So we have to be careful with this. The reaction there does not involve the equilibrium, and we aren't going to look at Kas or anything like that. We're just going to react our acid with the tris. Okay, so what we're looking at is ultimately a new equation. So we've got our tris plus our acid goes directly to our tris H. Okay. the process of doing that, what units should we be using? Okay, so molarity is a common concept, but we don't want to use concentration. Okay. When we do a non-equilibrium reaction, it's moles. It is the individual molecules that are reacting. So there's a variety of ways that you can present these calculations and try and organize it. If you've taken 152 and they've just used the standard textbook method, they usually use a before addition after kind of chart and then follow into an ice chart, okay? Or use the Henderson-Hasselbalch directly at that point. For people that have had me, I've gone through and slightly changed that a little bit into something known as the barn mice chart. So you're before you've added your strong acid or base. You've added the strong acid or base. It reacts, and then it neutralizes, and then we have to convert to molarity, and then you can ultimately process with your Henderson-Hasselbalch or your ice chart. Okay? So let's go through and process that out, and I'm definitely going to run out of space because that writing on the bottom, so I'm going to erase some of that. So before we add, so one of our important aspects here is that we have to remember the units we have to use are moles. Before we add our strong, do we know the moles of our tris? What are the moles of our tris? It's a yes and no. Okay. It's not directly given to us, but we do have to do a calculation. Okay. And we decided to assume that the concentration of our tris and tris H were the same, so we're going to run at our 0.1, really because I didn't want to make this even more complicated, moles per liter. Do we know the volume? We've got 0.1 liters. Man, I even did a unit conversion on it. Okay. Our liters can cancel, and we'd end up with the moles of our tris. Okay, so before we add any of our acid, we've got, what is that, 0.01? Okay. Before we add the acid, what's our acid concentration? Right, acid moles. There's no acid present. 0, and what's our tris H? Yeah, I know. What's the tris H?
0.
Not 0. Okay, so that was one of our initial statements that we decided to make from the very beginning. pKa equals our pH. For that to be true, looking at the Henderson-Hasselbalch equation, that term at the bottom needs to be equal to 0. And Carlos, just make sure you're looking in the right spot. Lower left-hand corner. See that arrow? Yeah. Your base and your acid have to be equal to each other, so that we know if our tris is 0.01, what's our tris H? It's going to be 0.01 as well. Okay. Then we follow this up with the addition of our strong acid. So how much of the tris did we add? How much of the tris did we add in this step? Nothing. All we're looking at is adding the strong acid. How much of the strong acid did we add? Now I think this is what you were talking about. We had 1 mole per liter times 0.03. Did I do that conversion right? Liters. So the moles of our acid added was right, 0.03. What was the moles of our tris H added? How much did we add of tris H in the process of adding strong acid? Nothing. We then allow these things to react with each other. Okay. Because this is a unidirectional reaction, it's only left to right, what we're going to do is evaluate our reactants and decide which one's our limiting reagent. Which one's our limiting reagent? Okay. Our tris is our limiting reagent, which means that's the one we're going to subtract. This was an awful example, by the way.
Isn't it 0.003 liters?
1 times 0.03,
Oh.
right?
Some milliliters to liters,
Yeah.
3 decimals.
I asked earlier, why don't you guys question it then? It's early. It is 3, yeah, because it's 100, yeah.
So that's
So this makes a little bit more sense with the numbers then. Good, my example isn't completely horrible. This is why I won't include calculations in it. I hate dealing with calculations. Whoops. So now what's our limiting reagent? Now that we kind of fixed that issue. Our limiting reagent is our acid. We'll subtract our acid from our reactant side, because it is going to react completely with the other species. Whoops. Depends how you want to format this as well. This is just generally how I like doing it. What happens to our product side? Anything happen to the product side?
You add it.
We're going to have to add it to the product side. Why do we have to add it? Yeah. What happens to the tris when we get rid of it? It has to become something. It's going to become the tris H. We can then look at the next step, which would be our neutralization. Hopefully I spelled it close enough to write. Our tris H is going to be our 0.01 minus 0.003. I saw some calculators out. What's that number?
0.007.
Maybe that was a bad question to ask. Our 0.003 minus 0.003. I do know this one. That one comes out as 0. And then our tris H will be 0.01 3. Yes? Good. What are the units on those? Moles. Okay, before we can deal with our pH, you didn't see that. Before we can deal with our pH, we have to realize that what we'd be either manipulating is either the Henderson-Hasselbalch or going through an ice chart. I'll tell you right now, we don't want to deal with an ice chart. Okay? So we want to deal with that. pH equals our pKa. To do that, we need to know the concentration of our base and acid. What numbers can we put in? Do we know the concentration of our base and acid now? This is one of those yes-no questions. We have the moles, we don't have the concentration yet. So before we can plug numbers into that equation, we need to convert our moles unit into concentration. So remember, at this point in the game, we are dealing with moles. The units on this number down here are moles. Same with this one, moles. L, thank you. How do we convert to molarity? So this would be the M of our barn mice. How do we convert to molarity? What's our volume? Good. Remember, we added some acid to this. We changed the volume. It's not just 100 milliliters anymore. So we have to divide our neutral amount by our total volume, which is 103, or 0.103. I'm not going to bother to actually calculate that. We've got moles over 0.103 liters and 0.013 moles. Whoops, pay attention. 0.103 liters. What is the A minus that we would be plugging into our Henderson-Hasselbalch? Tris or tris H? So our tris, what's our HA? Tris H. Okay. We can do our log of that, And we can add that to our pKa and we should get our pH. Is anybody crunching a number on that? Looks like you are, Heather.
8.02 for the pH.
8.02 for a final answer if you plug that into all the calculator. Does a number of 8.02 make sense? So before we sign off and verify that that's okay, the pH went down, we added acid, yeah, it should go down. How much should it go down by? Did we change it that much?
We added pretty normal.
Well, a little bit. Well, it's not even so much the concentration that we added, it's the moles that we added. So we're comparing 0.01 to 0.003. So we did drop it by a little bit, but our concentrations didn't change that much. We wouldn't expect a drastic change in the pH. We should still be in that buffer range. How do we know we're in the buffer range? We have a concentration of our tris and our tris-H. As long as we have substantial concentrations of those two, we should be in that buffer range. We shouldn't expect to see the pH shift much. Okay. Yes, no? Lab won't be examples that I'll just make up. So they should be a little bit cleaner, but we'll end up going through and solving very, very similarly as far as what's happening in the lab. Okay? So you want to figure out what you're starting with and slowly piece things together. If you're adding strong acids and bases, you've been taken out of equilibrium. You must address a pre-equilibrium reaction first. That's where we have to deal with the acid being added. In this case, the acid being added and reacting with the basic form of our buffer. And then we look at the change in the concentrations, use those new concentrations in our Henderson-Hasselbalch equation to go through and process what the pH would be. All right? What would happen if we added base? How would our reaction change? Our blue reaction change? How should that reaction change if we added strong base? We're adding, so one thing is the very end conclusion, what should happen to the pH? pH should go up. Okay, so we should end up with a pH higher than 8.3. Okay, what equation should we use to go through and figure out what all our stupid numbers are? The base is going to react with tris-H, the one with that acidic hydrogen. Okay? Kind of vaguely makes sense. Hopefully a few bells are ringing from 152. If you've not had 152 within the last, let's say, 2 years, you should definitely review it. Sit down with me outside of class and we can make sure that we can get you lined up with that. Okay? Questions? Yes.
What's the word above neutral?
Reaction. It actually just says react, but we're looking at a reaction. So it's before you add any strong acids or bases, you add your strong acid or base, okay, and that's going to change what reaction you're working with, so make sure you know which one you're adding. Okay. And then you do the reaction. The reaction is subtracting whichever one of those two reactants is our limiting reagent, so the smaller of the two. You'll then have to add that to the product side, because in the course of getting rid of your reactants, it has to go somewhere. So it's going to increase your product mole amount. You can then look at your neutralization. So you're just doing the addition of everything above it, okay, accounting for the signs. And then you've got to convert to molarity and watch out for any kind of volume changes.
So over here, you just plug in the A and the HA times the pKa that's given.
Use the pKa that's given. It's a plus in there. And you'd solve for the pH. How important is it to convert to the molarity at the end? You can kind of go back and forth on that. You end up plugging those numbers into your log expression, right? So let's say the volume was 1,000 1 over 1,000 divided by 1 over 1,000. What's your answer? Okay, let's change the number. Let's get rid of the fractions, make it a little bit easier. Okay, our volume is 1,000, so let's just say 1,000 over 1,000, because the volume of A is going to be the same as the volume for HA. So if our volume is 1,000 divided by 1,000, what's our number? So mathematically, it doesn't really hurt us if we don't convert to the molarity at the very end. Where it's really going to hurt you is converting out of molarity earlier on. Because when we run this equation, our blue equation, we have to be in units of moles to make sure that we're accounting for that proper cancellation in our reaction step.
So what you're saying is don't even worry about converting molarity, just take.
Don't have to stress about it at this
take
point.
Your numerator, plug it in as the concentrations.
Yep.
And run it.
And you should be fine. As long as you've gone through and done all those other steps, you should be fine. The reason why in 152, for those of you that had 152 with me, I stressed converting it into the molarity is because when we use this, what's our concentration thing at the bottom? Or the units for this are concentration. And there are certain problems that in a more simplified situation, you're given units of concentration, and if you're just plugged them directly in and you haven't accounted for volume changes, it becomes a problem. So if we go through and always remember to always convert into molarity and always convert out of molarity, it helps clean that up a little bit. Okay? Other questions with the mathematics?
Just to
Yep.
make sure, over here on the left would be the HA, and over on the right the A minus.
Right is HA. Take a look, you've got the hydrogen attached to the tris.
Okay.
So the right side is your HA, the left side was your A minus. The other way that you could look at this, we're adding strong acid. What does the acid react with?
A minus.
A minus. So what does tris have to be?
A minus.
It has to be A minus. Because the acronyms for our buffers tend to be very confusing, I will probably supply an equation saying this is the acidic form, this is the base form, to help you clarify with that, to make sure there's less confusion on the exams. Okay? What I am primarily concerned about with these buffer situations is how can you make a buffer. Okay? So if you're given the pKa of a buffer and you want a pH of your buffer to be lower than that, what do you have to do? You have to add acid. Okay? You're going to have to add a strong acid to get it to go to that lower position. I'm more concerned about the interpretation ultimately of what would really be a titration curve than dealing with all the raw mathematics behind it. Okay? Questions about that? One more quick thing, just in case this is a common trend. Px, how do I solve for Px? How do I solve for x?
Negative, yeah.
This is where you need to be careful. This is a mathematical quality that you would have to go back to. Okay? So to solve for x, what we can do is we can divide both sides by the negative. So we're looking at the negative px is equal to the log of x. Okay? I need to get rid of log. How do we get rid of the log? You need the anti-log. Okay? We can't just divide both sides by log. It doesn't work like that. The anti-log is the power of 10. So power of 10 to the negative px will equal power of 10 times log of x. 10 to the log of x equals x. Okay? This is how we can go back and forth between the concentration of hydrogen ion and the pH. Okay? One more equality that seemed to get missed If I give you H plus, what's its relationship to H3O plus? They're the same. Those are equal to each other. Okay? The only differentiation between those is H plus is ultimately kind of lazy. H3O plus is less lazy, but it's still officially wrong too. Okay? When you put an acid into water, you get a much more complex structure than just H3O plus. Okay? H3O plus is ultimately because we're looking at it being in water. Biochemistry, all of our solvents are going to be water. Okay? The other relationship, how can we relate H plus and OH minus? What's the relationship between those? So, biochemistry, it's in water by definition. And what were you suggesting, Scott? Okay, as long as we're in water, we know that the Kw, which is the equilibrium expression for the dissociation of water. So what happens when we look at the reaction of water dissociating? What do we get? Concentration of H plus the concentration of OH minus. If we now write out a K expression for this, we would get the concentration of H plus times concentration of OH minus. Remember our products over our reactants. As long as we make sure that our experimentation is done at a constant temperature, that constant temperature for Kw is typically 25 degrees Celsius. Anybody see any problems with using that Kw? What was that? Okay, water will be on the bottom, so what we'll end up doing is multiplying both sides by the concentration of water, which will stay constant, which is how we get the Kw equal to 10 to the minus 14. We got our H plus times our OH minus equals 10 to the minus 14. So if you know the H plus concentration, you can now solve for the OH minus concentration. Okay? Again, mathematically, why does this become obnoxious? Negative signs and exponents. Careful. Make sure you watch out for those values, particularly when entering it into a calculator. If you have one of the graphing calculators, those will be nicer because you can see your work as you're entering it and find those mistakes. If you're using a simplified calculator, particularly in Sapling, and you just kind of jump on their little calculator, it quite frankly sucks. You can't see if you've made a mistake, and it really takes some practice learning how to use those kind of calculators with exponents. Okay. Why is this Kw problematic for biochemistry? We're going to study a particular enzyme that's occurring or that's doing some reaction inside the body. Okay, we'll pick a buffer that doesn't interact with it. Good deal. What else could potentially affect the speed with which that enzyme works? Temperature. So if we change the temperature, what is that going to do to our Kw? Changes it, which means we're going to also end up changing the concentrations of our H plus and OH minus, which means we could possibly also change dynamics of our reaction. Okay? So this Kw, while it's probably the more relevant one, we end up doing some approximation saying it doesn't change enough if we're going to use it when running reactions within the body. Okay? Or we'll give you a new Kw. Questions? Please, God, no, I don't want to deal with any more math. Okay. It will come back and haunt us again when we look at enzyme kinetics. We won't see the numbers, but we will see a lot of graphical interpretation and rate relationships and fun stuff like that. Okay. So this is ultimately chapter 3 now. What we'll be looking at is amino acids as being kind of the building block or our Legos of proteins. So first we have to have some understanding of what our amino acids are. Amino for the amine side of our amino acid, and then the acid for the carboxylic acid other side of our amino acid. Okay. Our amino acids generate different physical properties based solely on the R group. Or not solely, but a large part of that R group. So depending on where we put that amino acid within an overall structure, that R group can determine whether it becomes active or inactive. Okay, so this would be known ultimately as our primary structure, which we'll look at in chapter 4. Your amino acids are your monomer within the polymer of your protein. We'll again look at this in a little bit more detail. How are our amino acids linked to each other? You're fine. It's not like the answer is on there. We're looking at a peptide bond, also known as the amide bond or amide bond, depending on your pronunciation. Okay? So that's how these things end up getting linked together. Anybody see a problem with that structure? What is special about that atom? It's chiral. Okay, it is a stereocenter, which means the orientation of that R group, depending on which direction it's following, will generate different potential chemistries. Okay, so we have to be very careful with what R groups we're dealing with. Okay, when it comes to amino acids, how many different stereocenters do we end up using? Human body, how many different stereocenters do we have? 1. Okay. Our body only focuses on that one type of stereocenter. It always comes out in that exact same chiral orientation. We don't see the other formation. Okay. That is one of the reasons actually why some people suggest a higher order or a higher power in life, because if we look at random probabilities of a reaction, if we were going to do a standard reaction where we started with no chiral center and then ended with one, our products end up being organic chemistry, racemic mixtures. We get a mixture of both. If there's nothing to favor one or the other, we only get, or we get both. Why on earth does it make sense, or why is it possible that we only ended up with one version for our proteins? Okay, so it seems a bit interesting. Yes, there are plenty of theories on it, but that's not going to make anybody happy. Yeah?
I was just going to say maybe there's something that we haven't discovered yet that makes it so that it is favorable for only one.
So yes, but then the very next question you'll get is, where did that come from? Why is that only in one conformation? So one of the arguments that I've heard is that quartz that you'll find in mineral deposits is chiral. Okay? The quartz crystal itself is chiral, so depending on which one was predominant in that area, we may very well have generated life from quartz, or that handedness coming from a quartz. So it's kind of interesting. You'll notice this fun conformation. So what we've done is switched or changed the orientation of how we're looking at that first molecule to represent better that three-dimensional characteristics. Our wedges mean coming at you, and the dashes mean going away. What kind of drawing did I just generate with these two? We're looking at Fisher projections. Right? Why did Fisher go through and change it? Pretty much because he could. The Fisher projections work for much more complex structures. When you're looking at sugars, which we'll look at, I think, in our second section, it becomes a lot more easy to see the relative orientation. And when you change the orientation of your primary groups, you can see the switch between the different chiral centers very, very quickly and effectively, without having to go through and check each one and determine this one's R, this one's S. You can say, oh, it's changed. That means it's a different sugar. Okay, so the Fisher projections can be helpful. Some notes on drawing Fisher projections. Your carbon chain is always aimed vertical. So we'll find the longest carbon chain, and that is the one that's going to fall on the vertical axis, your y-axis. And then we'll always put our highest priority group on the top. So in the case of the amino acid, we're looking at the acid functional group up top. When we take a look at carbohydrates, it ends up being an aldehyde, okay, or ketone. as close to the top as possible. Right? The next part of this is deciding what the chiral center is. Okay? You'll notice that we could use a variety of different options. The one that we're going to use is L and D. Okay? What does that L and D stand for?
Levo and dextro.
Kind of. What we're looking at is where the amine group is located, be it on the left side of the structure or the right side. So it was nice why you said the levo and dextro, okay? Because it's not a rotatory issue. It's just left and right side of the structure, right? Why is that a bit odd? Have you heard of L and D before? Yes. When we look at L and D in those other cases, is it capital L and D? Lowercase L and D. The lowercase L and D are in reference to how it's rotating light. The capital L and D is in reference to glyceraldehyde and how these compare towards glyceraldehyde. Okay? Yeah, that's not, a natural correlation, but that's where it's coming from. Okay, it's a bit silly. I think they pick up one possibility. So why do we not see that lowercase L and D? Well, those are ultimately rotations of light. This isn't a rotation of light. It does happen to translate, actually, but this isn't where that came from. Our capital L and D are in reference to how they compare to the structure of glyceraldehyde.
I've never seen the lower cases that's on this part.
The lowercase L and D you would typically only see in organic chemistry, and most tend to avoid that, kind of like the plague, because it's very easy to get it confused. You'll typically also see the plus and minus. The plus and minus are again in reference to
Levo and dextro.
levo and dextrorotatory, how it rotates light, okay, either in the positive or negative direction from your zero axis. R and S, okay, that is an absolute configuration when we look at the structure given. Why did we probably not come up with R and S when we first looked at amino acids? No, we said there was only one.
Because there's only one?
R and S are based on the structure. Did we have the structure? Really all we had to work with was a pure molecule, glyceraldehyde, and we noticed how glyceraldehyde responded to light. Right? We then compare other things to light, said it either matches glyceraldehyde or it doesn't. Right? There was no absolute structure configuration. Not until we could figure out what our absolute structure was could we really use R and S. Okay? Bit obnoxious, but that's the way it works. Okay? Questions about that? Just kind of my personal peeve on this. What's the difference between, if we look in the upper right-hand corner, what's happening up here? Are those interchangeable? No. Those mean two different things. Okay? Your textbook is using them interchangeably. The textbook was written very clearly not by an organic chemist. Okay? So be careful with that. If you're seeing that dash, that means it's going away, and then it's going to be difficult to kind of interpret which atom they're saying is going away. Okay? So kind of watch out for that issue. Hopefully you'll see it only when you're looking at the Fisher projections, and your Fisher projections are always aiming those carbons away. So even if you happen to see this dash get switched around on you, if we saw something like this, okay, the R group is still away. Okay, so kind of watch out for that notational issue. It shows up fairly rarely, but depending on where you see it or use it. So what it's referring to is our atom in front is our smallest dot. Okay, the atom that's behind gets our largest wedge.
Okay.
Okay. If we go through and look at this one, in this case now our carbon is behind, our nitrogen is in front. Okay. So just kind of be aware of those kind of oddities, just in case you do see them. So our amino acids, we've got 20 common ones. You've got the name, you've got the 3-letter combination, and then you have, a 3-letter code and a 1-letter code. right? In any biochemistry class, or most biochemistry classes, you would be expected to memorize all of them. We're going to tweak back away from that a little bit. I expect you to memorize 5. Within those 5, you should pick 5 of varying physical properties. Right? Don't just pick all the exact same type of amino acid, which we talked about a little bit last week, and we're going to look at that again today. Within those 5, you need the name, you need the 3-letter code, and the 1-letter code. So when it comes to the exam, I will expect you to be able to pull on your memory, right? And you might be able to cheat because I might give you the structure of a few amino acids on there, and you might be able to use those instead. Right? But you should work on nailing down 5 amino acids. Right? And then I want you to know something about their structure. So that if I refer to, let's do isoleucine. Where would you expect to find isoleucine? On the inside or the outside of a protein? You all memorized your amino acids already, right?
Of course.
Okay. Being able to decide that relies on a couple different things. Number one, what's the physical property inside a protein? This really only works for those of you in lab, so those of you in lab can help out with this. What physical property is primarily found within a protein versus on the surface? We're looking at hydrophobic interiors of a protein and hydrophilic on the outside. So if I ask where isoleucine is located in a protein, or where we would typically find it, what do you need to know? Number one, the inside of the protein is hydrophobic and the outside is hydrophilic. And then number 2, you have to know what the R group is on isoleucine. Right? You need to know what it looks like so that you can predict, is it a hydrophobic group or is it hydrophilic? So that you can then put it into the correct category. Okay? That was a very targeted question. More than likely what you would see on the exam is pick 2 amino acids, or pick an amino acid that you would typically find on the inside of the protein and pick an amino acid that you would find on the outside. Okay? Give me the 3-letter code. Okay? For the homework, as far as the homework goes, look them up. Okay? You're not expected to just have everything memorized. The homework is there to be practice and get you to make sure that you've been reading the textbook and finding some extra information somewhere. Right? So feel free to look them up when doing homework. Yeah?
How would you know what variation of the amino acid you would find in different pHs?
We'll talk about that in a little bit. But yeah. So first thing I want to do is go back to that kind of activity, that we looked at briefly last week. What does the base need to have? It needs to have electrons. Okay, good thing to look for would be a negative charge. Okay, so if we find a negative charge, we say, oh, that acts as a base. Except what's the problem with a lot of our amino acids? They're all acidic and basic.
Depending on which end you're looking
And depending on what pH you're at, it might be negative or neutral. So in particular, if we take a look at, I don't remember what D and E are. Do you get the structures of those two?
Which one?
There we go, that's what I wanted. We take a look at what Carlos labeled as basic for E, and we look at that structure. What's the overall charge?
Overall?
Overall,
Negative.
it's negative, which would seem to suggest it would act as a base. How is that amino acid actually classified?
Acid.
It's classified as an acid. Why is it classified as an acid?
Different.
Right. Because if we look at just dissolving the amino acid in its fully neutral state and put it into solution, it gives off a hydrogen. That functional group at the very end, off the R group, looks a lot like carboxylic acid. So deciding whether a group is acidic or basic or not isn't as simple as just looking at the structure. It's also really important to look at the pKa's and evaluate what's going on with those. Okay? And I'm going to look quick me see if I can't find another one in here. I believe it's tyrosine. Yeah. What functional group is on tyrosine? It's Y. We're looking at a phenol functional group. What's the acidity of a phenol functional group? Phenols are typically acidic. Right? So this is one that I probably would have slid into an acidic category because I know from organic chemistry that it's an acidic compound. Is it placed in the acidic category? No. Why is the phenol not typically placed in the acidic category? Because at standard pH, it still has the hydrogen attached. At physiological pH, the hydrogen is still there. So when we're looking at the categories that are typically used in your textbook, it's not just the functional group, but it's looking at what happens at physiological pH. Okay? Is a hydrogen attached or not? So the primary categories that typically get used, we get 4 of them. We'll just address some of them. Acidic and basic. And then we've got our neutral polar and neutral nonpolar. For it to be an acidic functional group, what you're looking at is a negative charge at physiological pH, so pH 7, roughly. Right? For it to be a basic functional group or a basic R chain, what charge does it need to be? If it's basic, it's accepted a hydrogen. We're looking at our nitrogens, it picks up a positive charge at pH 7. Okay? Typically, when you look up the structure of an amino acid, the structure is given at what pH? Where are we typically going to look at amino acids? In the body, we're looking right about that pH 7 line. Okay, so when you look at the structures, be aware, you may look at it and say, well, there's nothing there for it to be acidic. Why is it acidic? Okay? It's acidic because at that pH, it already lost its hydrogen. Okay? The other 2 categories, you'll notice both of them are neutral. Why would we kind of subcategorize those into polar and nonpolar? Where would we find the polar side chains? Outside the protein. Nonpolar, inside the protein. That's a pretty drastic difference on where we would find them. So these are our primary categories. With our neutral polar, what atoms would you expect to find in our neutral polar for the side chains?
Oxygen, nitrogen.
We would expect to find oxygen or nitrogen, not charged. So in our phenol, we don't have that negative charge. All right, so these are all going to be neutral charged at this pH. What else might you find there? One more. Is chlorine an amino acid, though? In an amino acid?
Sulfur?
Sulfur. Sulfur is nice and large. That large size helps it dissolve in water well. Okay. And our neutral nonpolars, our R groups are primarily just carbons and hydrogens. Okay. Depending on other environments, perhaps one of those polar side chains is then buried behind a bunch of carbons. Now you've hidden effectively that polarity, and that R group starts to act more like that neutral nonpolar. Okay. But these are the 4 primary categories that you'll see in your textbook, and things will vary off of this, but realize they are variable. I mean, all you got to do is check what everybody else listed off as their possible side chains. So be aware of those kind of limitations within those categories, and make sure you're aware of how you would predict them to be. So our primary goals are where they would show up in your protein. Other things you could look at is reactivity, in the sense of acids or bases. Right? And lastly, you could also look at solubility, perhaps even in water. Okay? For instance, if we had a bunch of side chains or a protein that was primarily neutral nonpolar amino acids, would we expect it to dissolve in water? Nope. So more than likely, that amino acid or that protein would be involved with what? It's kind of a trickier question.
Inside of the chain.
So it could be inside of a protein, yeah, but we're saying it's not going to dissolve in water. So what would be something, why would we want any kind of protein to not be soluble in water? It can be part of something that's more rigid. Okay? We don't want it dissolving and shifting somewhere else. We want it to stay in one location. We want it to hold its function, hold its shape. So we could look at proteins that are involved in shape characteristics, cell walls. Okay? Those are going to be designed to be as rigid as possible. Okay? Questions about categorizing these guys? Okay. All right, definitely did this one. Oh, maybe not. What's the pKa of your carboxylic acid, roughly? Carboxylic acids are typically around 4. We're putting our carboxylic acid in the, and let's see, do I have a structure on this? Yeah, I do. We're putting our carboxylic acid darn close to an electronegative nitrogen. Okay? And in particular, in the amino acid, not only is it an electronegative nitrogen, but it's a nitrogen that is positively charged. Does nitrogen want to be positive? Nope. So its inductive effect from that nitrogen becomes even stronger, which means the amino acid, or the acid portion of our amino acid, becomes even more acidic. The pKa typically drops into that 2 range. So for nearly all of our amino acids, the pKa of your carboxylic acid is about 2. I think the average maybe is 2.2, according to your textbook. What about the ammonium? It's about 9. All right, so we're going to end up with that ultimate reactivity for all of our amino acids. Our side chains can potentially contribute some pKa characteristics that's going to balance somewhere between those. Okay? So all of them minimally have these 2 acid-base sites, which is what we would need anyway, because to build a protein, we have to be able to connect these amino acids near each other, which means we need 2 reactive sites to be able to link. Okay? And then we could potentially find those other ones in our R groups. Let me make sure. I wanted to draw something there. Oh, oops, kind of. If we take a look at the 2 structures that are drawn up here, at low pHs, what happens? So we're in a very, very acidic environment. What would happen to our nitrogen? It should pick up that hydrogen. Remember, your amines are typically basic. So if we're at a very low pH, oops, I got rid of my pKa. Our pH is lower than our pKa. What happens? We put the hydrogen on. Okay, so we'd end up with our positively charged amino group. What happens to the carboxylic acid? Again, if we're at a very low pH, we're typically lower than our pKa. Say we're at a pH of 1 in that low pH situation. The pH is again lower than our pKa for our carboxylic acid. And what do? Put the hydrogen on our structure. What happens if we push the extreme? We go to a pH, I feel like a sneeze is coming. pH up in 10, let's get really crazy with it. Let's make it a 12. Okay, what happens now? Okay. First we would address our carboxylic acid. Our pH is greater than our pKa, which means remove the hydrogen. So take the hydrogen off of our carboxylic acid. What charge does it become? We got our negative. If we take a look at our pH and now compare the reactivity at our ammonium site or our nitrogen. Right? If we now go ahead and look at our pH is again bigger than our pKa, which means again we need to remove the nitrogen. So we remove a single nitrogen, or sorry, a hydrogen from our nitrogen, and what charge does our nitrogen become? Neutral. Okay, so those are our 2 extremes. What happens is we slowly titrate acid into this. Okay. So at some point, let's increase the pH up to, let's go physiological pH. pH equal to 7. We've got our amino acid structure, our R group, our hydrogen. Okay, we want to address the chemistry of our structure at pH 7. Okay, our carboxylic acid pKa we said was roughly 2. So our pH being greater than 2 means remove the hydrogen from that functional group. So we go up to our carboxylic acid and we remove the hydrogen. What charge does our oxygen become? Negative. Address the chemistry around our ammonium. We said the pKa was roughly 9. We're at a pH of 7. Our pH is less than our pKa, which means the hydrogen should stay on. So we leave the hydrogen on there. Notice that we now have our amino acid at pH 7. This is typically where all of your amino acids are drawn out as far as their structure. So if you look at the little note card things, that carboxylic acid functional group has a negative charge, and the nitrogen has that extra hydrogen on it to be positive. This structure carries a particular name. The next slide, you probably have the answer. It's known as the Zwitter ion. Okay? Because it has those 2 charges. It's German, 2 charges. Close enough. Okay? So what we're looking at is that Zwitter ion species. Okay? So let's push it to an extreme. Let's look at tyrosine as an example. So what we'll do is pick the extreme acidic pH. Now, this is kind of the standard notation to start at your completely acidic. So we'd start really low at a pH 1, and we'd slowly increase the pH by adding base. Eventually what happens? One of our functional groups is going to react. Whoops. Darn it. Copy paste. pH 1, our carboxylic acid, should be protonated, right? Should have that hydrogen on it. Okay. As we slowly increase the pH, one of those acidic functional groups is going to react. Which one's going to react first? The most acidic functional group being the carboxylic acid. So we should remove that hydrogen, which would mean what about its pKa relative to the others? Higher or lower? It should be the lowest. Oh, what? Damn you. All of those boxes were supposed to stepwise out. There's a whole bunch of structure drawn under that. We're definitely over time, so I'll go ahead and stop. And we'll pick up with that one, looking at that titration with an amino acid all the way through. Why would we expect to see 3 reactions in the case of this amino acid? You can pack up. There's 3 functional groups that have reactivity. Your phenol, the carboxylic acid, and the amine.